Good morning, my Ohmies. Welcome to Chillin' with My Ohmies for another episode. My name is Jordan. Today we're going to be talking about capacitors. This is part of a series I'm starting on this channel where every few days I'm going to be explaining the electrical properties and how different pieces of electronics work that gives us our ability to make things like nuclear fusers, Tesla coils, Jacob's ladders, and everything. All electronics. So today's episode, of course, is capacitors. Capacitors are an incredibly interesting, incredibly dangerous, with the right capacitor, component to be messing around with. So what is a capacitor? Well, come over here. This is the electronic symbol for capacitor. If you can recognize something, we have a wire here, another perpendicular line, an empty spot, perpendicular line, and a wire. Why is that? That's because capacitors are an open circuit. There is no electrical connection between here and here. Therefore, it is insulated. And we call the insulator in here, whatever that may be. It could be mica, it can be ceramic, it can be electrolytic, it could be air, it could be anything. So a capacitor is any two electrical conductive things, anything, separated by an insulator, even air. So if you hold two quarters up and put them close to each other but don't touch them, technically that is a capacitor because it's two conductive surfaces separated by an insulator, or called dielectric. There are two types of capacitors. We've got this one here. This is a rather large capacitor, if you can see that. This is a ceramic capacitor. It has very low capacitance, meaning it can hold very little charge. And that's what capacitors do. They hold potential energy in an electric field. So, to explain that, if you put positive voltage here, and we'll say this is grounded here, what happens is electrons are going to start building up on the negative side of the capacitor where you're putting voltage. On the positive side, ions or holes will start building up, positive ions. And it is a static charge, just like the static electricity you get shocked with after you rub your feet and touch a door handle or whatnot. There's a static electricity here. And the longer you put your positive power here, your ground here, it charges. And it charges at the rate of R times C, resistance, not of the capacitor, but resistance of the input. So the resistance of the input times the capacitance equals the time in seconds it takes to fully charge that capacitor. I say fully, where it's actually around 91%. Once it hits 91%, it charges slower and slower and slower. And the reason is less and less spots are available for electrons. So think of it like a parking lot. If there's a lot of spots, you can put a lot of cars anywhere quickly, but when the parking lot's filled up, it's harder and harder to get those charges or those cars to a place to park. So, what does this mean? How do we use this? Well, there's a few uses for capacitors. The smaller ones, like the one I just showed you, are mainly used for filtering. So AC, alternating current, passes through a capacitor. According to AC, not DC, a capacitor is more of a resistor than it is a open circuit. You might be thinking, why can AC pass through but DC can't? Well, AC passes through because imagine this plate of the capacitor is a transmitter antenna. Imagine this plate of the capacitor is a receiver antenna. And they're both very, very close to each other. Therefore, AC flows through. And we can see the reactance or or the impedance, the total opposition to current of a capacitor in an AC circuit, as this. Reactance is equal to the reciprocal of 2 pi F for frequency, C for capacitance. So the higher capacitance we have, less reactance. Higher frequency the AC is, less reactance, easier it is for AC current to flow through. So one of the reasons you use a capacitor is for a filter. Say you want DC. You want DC on your line, but you don't want AC. If that's the case, you just put the capacitor to ground and your DC supply here, and then pass the current along to your load. Well, AC is not going to go towards your load. Say here's your load. It's not going to go towards your load. It's going to actually find its way to ground, where DC can't pass through that capacitor, and it goes to your load instead. That's a way to get rid of AC in your circuit. It's also called decoupling capacitors. So we see them a lot in filtering, getting rid of AC, or on the other hand, where you can block DC. Say you're running an amplifier, you don't want DC through, you want your AC wave through, then you use a capacitor to block the DC and allow your AC to pass. The other thing they're used for mainly is resonance circuits, so resonance frequency. So if I have a capacitor, and I also have an inductor, which is just a coil of wire, we'll talk about those later. Capacitor and inductor will resonate, meaning the capacitor will discharge into the inductor, once charged, will discharge into the capacitor at a certain rate defined by frequency is equal to the reciprocal of 2 pi multiplied by the square root of L, which is inductance, and C, capacitance. Capacitance, of course, I should have mentioned this earlier, is measured in farads. And you'll usually see it in microfarads, as capacitance works out in equations to be 0.0000, very small numbers. But what I really want to hit on today with capacitors is not about their filtering aspects, or it's not about their resonance frequency capabilities, which are very important in many circuits, including a Tesla coil. What I want to talk about is the danger and, by extent, the fun you can have with them. So this is also a capacitor. You notice I have it shorted, and the reason I have it shorted is because charges in the air on high capacitive capacitors can build up and put a voltage on there. Capacitors are special in the way that even once you remove power from them, they stay charged, and they can stay charged for days, weeks, months, good ones even years. So even though you've turned off your circuit, that doesn't mean that this still can't hurt you. This is a capacitor, especially the big ones. Think of them like a bucket. Not a bucket for water, but a bucket for electrons, an electric charge. And so similar to a battery. And you can use this bucket, you can fill this bucket to the brim, and then quickly discharge it. Quickly discharging a capacitor is like, what analogy do I want to use here? I guess it would be cranking up a jack-in-the-box. You put more and more and more and more tension on it, and when you're ready to short the terminals and discharge it, it can discharge your capacitor at an extremely fast speed. There's almost no internal resistance to these things, meaning when you short them, when they're powered up, when they're charged or powered up, the bucket's full, and you short them, they dump almost all of their power at once in a large, spectacular boom. It's very fun to see. It's a very cool thing, and I will be stitching together this particular capacitor, or one like it, discharging at the end of this video. So stay tuned for that. I also have, which I'll edit in, some of these. These off screen here are enormous capacitors, by the way. They have a tolerance, meaning capacitance, the amount of voltage you can give it before it shorts, of 50,000 volts. 50 followed by 30 volts. That's insane. Not only do they have that, they have the ability to output 9.125 kilojoules. 9,125 joules each. This one here gives off about 1,000 joules. You can shove it full of 1,000 joules of energy and discharge it almost all at once. Very, very short amount of time. And that amount of energy being shorted is incredibly spectacular thing to watch. You can destroy things with it. You can crush coins. You can do a million things with discharging capacitors. In fact, that's how you build a rail gun. That's how you build a coil gun. You charge your capacitors like this guy here, the two big ones I just showed you, and then dump all their energy at once by giving a low resistance across the terminals. And it's a very spectacular, very good thing to do, and it's going to be my next big project with the two giant ones I just showed you. So, how do we know how much energy a capacitor could store? Well, it goes by this formula. Energy in joules is equal to 1/2 of capacitance multiplied by voltage squared. So, I have this capacitor, you can read it there, is rated at a maximum of 400 volts. So 400 volts squared would be 16,000 right here. Well, 16,000, after you square it, and you multiply the capacitance, which this is 12 millifarads, not micro, millifarads. So I take 0.012 for milli, multiply those two together, and then I divide the whole thing by half, or multiply by half, divided by 2, and I get 960 joules of energy out. Just for reference here, that's about the same as your average hunting rifle as far as amount of energy. And so we'll say this is about a kilojoule of power of energy I can get out of this thing when I short it. Well, guess what? I got 11 of these things. Yeah. So that's that's almost, well, actually, it's a little over 10,000 joules of energy. That's an insane amount of energy. And the giant flash capacitors that I showed you earlier in the video, those ones I have in my basement, together they can dish out over 18,000 joules of energy. Enormous amounts of energy. And the biggest thing you have to take away from it, while it's spectacular, while you can do a lot of things with them, it's incredibly dangerous. Incredibly dangerous. And they don't make a noise. They don't emit light. You can turn power off. They still have that energy in them. They still can dish it out the second you connect those two terminals, either with a piece of metal or your body. And they will dump all those joules of energy across your body and almost nothing flat, and it's very, very dangerous. That's also why, if you're working in any electronics, so you have some sort of electronics open and you find capacitor in there, even if they're not this big, a good thing to do before you start working on anything, even though it's unplugged, power's down, capacitors can still hold their charge. So what I recommend doing is taking a multimeter and probing larger capacitors in the circuit you're working on with a DC voltage. The internal resistance of the meter will slowly discharge any capacitor that has power. And it'll also give you how many volts it has as the discharge. Some say just short it, dangerous. Some say just put a resistor across it. Well, then you don't know when it's fully discharged. The safest way is, as long as your meter can handle the voltage of the capacitor. Most meters can only handle 1,000 volts. If you have a more powerful capacitor, you're going to need a high voltage probe. You're going to want to put your meter across it and slowly watch it drop to zero. Don't think because you turned it off, because you unplug it, you're safe. Things like this in there can dish out quite a bit of power, can give you quite the shock, and in certain circumstances where they're a high enough voltage and high enough capacity rating, such as this guy or the two big ones I just showed you, they can kill you without any warning. So be very careful. But there you have it. That's my little lesson today on capacitors, the do's and what they do, what their uses are, what they are, what I have them for, what I'm going to use them for, and what's to come, and of course how to be safe around them. So, thank you for watching this video. I plan to do more videos on different components that are inside many of my experiments, many of my builds, and explaining what each and every one of them do. So stay tuned for more. Thank you and have a good morning.